handling areas below the x-axis. Welcome, everyone. Today, we are going to build upon what we have already learned to tackle a very important nuance in calculus. In our previous lessons, we established a fundamental rule that the area under a curve, where y equals f of x, can be found by integrating that function over a specific interval. This worked perfectly as long as our curve stayed above the x-axis. However, as we move into this new topic, we need to be very careful. A critical distinction must be made between what we call the value of a definite integral and the physical area of a region. It might seem like they are the same thing, but as you will see in the next few slides, they can actually be quite different when the curve dips below the axis. Let's dive in and see why. Understanding the concept of signed area. Now that we've established that integration is our tool for finding the area under a curve, we need to address a very important distinction. In mathematics, when we calculate the definite integral from a to b of f of x dx, we aren't just finding area, we are actually calculating what we call the signed area. Let me break down what that actually means for you. If the curve f of x lies above the x-axis, meaning f of x is greater than 0, then the integral will yield a positive value. However, if the curve dips below the x-axis, where f of x is less than 0, the integral will yield a negative value. Now I know what you might be thinking, but teacher, how can an area be negative? This is where we have to separate pure calculus from geometry. From a geometric perspective, area is a physical quantity, and a physical quantity can never be negative. Think about it this way. If you were measuring the area of a piece of land or the surface of a painting, you would never tell someone that the area is negative 50 square units. That just doesn't make sense in the real world. So, here is the key takeaway to remember before we move on to the mathematical solution. When a curve dips below the x-axis, the definite integral still gives us the correct magnitude, or the size, of the area, but it attaches a negative sign to it. We'll learn exactly how to strip that negative sign away in the next slide. The mathematical solution, absolute value. Now that we understand why the integral can return a negative value, let's look at the mathematical solution to fix this. To ensure that our calculated area is always a positive value, we use the absolute value of the definite integral. Think of the absolute value as a tool that simply strips away that negative sign, leaving us with the actual physical area of the region. So, if we are looking for the area, which we will call capital A, of a region bounded by the curve y equals f of x, the x-axis, and the vertical lines x equals and x equals b, specifically in cases where the curve is dipping below the x-axis, the formula is area equals the absolute value of the integral from a to b of f of x dx. Alternatively, if you have already confirmed that the curve is below the axis, you know the integral result will be negative. In that case, you can also express the area by simply placing a negative sign in front of the integral from a to b of f of x dx. This negative sign effectively cancels out the negative result from the integration, bringing us back to a positive area. In the next slide, I will show you a step-by-step procedure on how to apply this logic to a real problem. Step-by-step procedure to calculate area. Now that we understand the theoretical difference between a signed integral and a physical area, let's talk about how you can actually apply this in your exams. I don't want you to feel overwhelmed by complex graphs. Instead, I want you to follow a consistent, 4-step procedure to ensure you never miss a sign error. Step 1 is all about analysis. Before you even pick up your pen to integrate, you must analyze the function. Your goal here is to determine if the function, f of x, is positive, negative, or if it actually changes sign within your given interval. From a to b, a great tip for this is to simply plug in a test value from within that interval, or better yet, quickly sketch the graph. This prevents the mistake of treating a negative region as a positive one. Step 2 is setting up the integral. Once you know where your curve lies, write down your definite integral using the given limits, a and b. This is where you translate the geometric problem into a mathematical expression. Step 3 is the evaluation phase. This is the standard calculus part where you perform the integration using the fundamental theorem of calculus. You'll find the antiderivative and subtract the value at the lower limit from the value at the upper limit. Finally, step 4 is the most crucial step for this specific topic. Apply the absolute value. As we discussed in the previous slides, the integral might give you a negative result if the curve is below the x-axis. If you see that negative sign, don't panic. Just take the absolute value to convert that magnitude into the final physical area. In the next slide, we are going to walk through a concrete example together, applying these exact 4 steps to see how it works in practice. Illustrative example. Here is our problem. We need to find the area of the region bounded by the curve, y equals x squared minus 4, the x-axis, and the vertical lines, x equals 0 and x equals 2. Step 1, we must analyze the position of the curve. Before we start calculating, we need to know if this curve is above or below the x-axis between 0 and 2. To do this, let's pick a simple test value within our interval, say, x equals 1. When we plug 1 into our function, we get 1 squared minus 4, which equals negative 3. Because this result is negative, we have confirmed that the curve lies below the x-axis in this region. Step 2, now we set up our integral. Recalling from our previous slides that the integral gives us a signed area, we must use the absolute value to ensure our final answer represents a physical area. So, our formula for area A is the absolute value of the integral from 0 to 2 of the function, x squared minus 4 dx. Step 3, next we evaluate the integral. First, we find the antiderivative of the function. The integral of x squared minus 4 dx is x cubed over 3 minus 4x now. We apply the limits of integration from 0 to 2. We plug in the upper limit 2 to get 2 cubed over 3 minus 4 times 2, and then subtract the result of plugging in the lower limit 0, which gives us 0 cubed over 3 minus 4 times 0. Simplifying the upper limit, we get 8 thirds minus 8. Subtracting the 0 part, we calculate 8 thirds minus 24 thirds, which leaves us with negative 16 thirds. Step 4, finally, we apply the absolute value. As we learned earlier, while the integral result is negative 16 thirds, physical area cannot be negative. Therefore, we take the absolute value of negative 16 thirds, which gives us our final answer, 16 thirds square units. Now that we have covered the theory and the step-by-step procedure, let's put everything we've learned into practice with an illustrative example. Let's walk through the solution together using the 4 steps we just discussed. As we move to the next slide, keep in mind that this negative sign is exactly what we need to watch out for to avoid common mistakes. Common mistakes to avoid. First, please be careful not to confuse the value of the integral with the actual area. I have seen many students perform the integration perfectly, reach a negative result, and simply stop there. Remember what we discussed in slide 2. While the definite integral can indeed be a negative number, a physical area, just like the area of a room or a piece of paper, can never be negative. If you see a minus sign in your final result, you haven't finished the problem yet. Second, do not ignore the graph or the position of the curve. It is vital to check whether your function is above or below the x-axis. If you fail to check this, you might miss the fact that the curve is dipping into the negative region. This is especially important for more complex problems where the curve might cross the x-axis, a topic we will cover in our next session. Always take that extra moment to analyze the function's position, just like we did in our example. Finally, watch out for incorrect sign application. A common mistake is to blindly multiply your result by -1, even when the integral is already positive. You should only apply the absolute value or the negative sign if you have confirmed that the curve lies below the x-axis. If your integral is already positive, leave it as it is. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. Even if you understand the concept, it is very easy to make a small error that leads to a completely wrong answer. Keep these points in mind as we move into our final summary. Key takeaways. First, it is vital to remember that the definite integral, from a to b of f of x dx, does not always represent the physical area. Rather, it represents what we call the signed area. This is the core distinction we discussed at the beginning of the lesson. Second, keep in mind that when the function f of x is less than 0 for all x values within the interval from a to b, the result of your integration will naturally come out as a negative number. Third, because we are dealing with geometry, we must remember that physical area is always a non-negative quantity. This is why, as we saw in our step-by-step procedure and our worked example, we use the absolute value of the definite integral, from a to b of f of x dx, to find the actual area. Finally, my best piece of advice for your exams: never jump straight into integration. Always verify the position of the curve relative to the x-axis first. Checking if the function is above or below the axis is the only way to ensure you don't fall into the common mistakes we covered in the previous slide. All right, we have reached the end of this lesson, so let's wrap everything up by reviewing our key takeaways to ensure you have a solid grasp of the concept. If you have mastered these points, you are well prepared to tackle more complex problems where the curve crosses the x-axis, which we will explore in our next session. Great job today!